Hello, welcome to AQA Physics 2018. This is paper 2, higher tier. So I pasted this into Word so I can write on it. So if you can't write on the PDFs you find online, you can paste the images into Word and you can look at them and write underneath them. That's what I've done with this. So I recommend you to do the same thing if you'd like to practice the exam paper alongside. Okay, doesn't require any certain software or anything. So I found the paper online, and that way you can actually follow along with me. Okay, on the paper. So I've just pasted it into Word. So let's do this. So number 1. So a child drops a ball. The ball hits the ground and bounces. Figure 1 shows the velocity time graph for the ball from when the ball is dropped until when the ball reaches the top of its first bounce. Air resistance has been ignored. So mostly in physics, we don't really talk about air resistance unless it explicitly states it. Okay, so you've got velocity in meters per second on this axis. It's not that obvious. So it's on the y-axis, velocity, and time in seconds is on the x-axis. So time usually is on. Okay, so the velocity is increased and suddenly decreased. Okay, so also, if you notice, velocity can be negative too. So let's think about what that means. Velocity is negative. So it's to describe the motion of the ball between points A and B on figure 1. So just A and B it's asking for, and that's 2 marks. Okay, so A and B. So it's velocity. So the velocity is increasing at a constant rate, therefore it is constantly accelerating. Sometimes it's also called uniform acceleration. Uniform acceleration. Okay. That's 2 marks, increasing. So actually, you only need one sentence there to give you 2 marks. So what direction is the ball moving between the points C and D on figure 1? So it's skipped out the middle section, so it's got to be careful of that. So C and D, okay, let's have a look at what's actually happening. The ball is dropped until when the ball reaches the top of its first bounce. So that's the top of its first bounce. So it must be moving upwards. So it's more making sure you've read the question there to answer that. So it's quite, obviously, because it looks like not quite straightforward what direction the ball's moving without reading. So if you want to write on a word and put an insert text box like I did there. Okay. So the ball and the earth form a system. What is meant by a system? Tick 1 box. So is it a group of objects that interact? Objects with big differences in mass? Objects with gravitational potential energy? So they don't have to have a big difference in mass. Sometimes they do, like the solar system, but they don't have to. They can have the system could be snooker balls on a snooker table. They're all pretty the same. That's a system. So gravitational potential energy, they don't have to have that. So the only one left is a group of objects that interact. So I have to put a tick. Oh, see, I needed a cross then, so I have to be a bit vigilant. Okay, a group of objects that interact. Do a tick. I'm going to do a cross. There's a tick. That's a tick. Okay. So when the ball hits the ground, energy is transferred from the ball to the earth. So when the ball hits the ground, so again, we've got to look at the context there. Energy is transferred from the ball to the earth. Explain how the data in figure 1 shows this energy transfer. So let's go back up again. Okay, so it's this point, B, when it hits the ground. You can see the velocity actually it instantaneously changes direction there. Okay, so from the graph, let's just go back a bit. So the velocity, let's write it down before we continue. Velocity just after the bounce is less than just before the bounce. That's one thing. We'll write about a few more things. Let's look up that, because yeah, again, it's not quite obvious. So it's velocity at this point. So if we go, this is in 6.2, 6.4, so it's in 6.57, so it's 7. It's about 7 here. Okay, but it's not even, so this negative means a direction. It's not, so negative velocity is different directions. The same, it's a difference in direction rather than going back in time or something. It's the difference in direction. So just before the bounce, it was about 7 meters per second, but afterwards, it's about 5, but just in the other direction. So that's one thing that we wrote down already. The velocity just after the bounce is less than just before the bounce. Therefore, it has transferred energy. Okay, so let's write that. So it has transferred, I wouldn't say energy to the surroundings. You can say the ball's lost energy, but you have to put also lost energy to the surroundings. Okay, so because this is about energy can't disappear. There's another one as well about the height. Okay, so the height actually, but yeah, it's probably a little bit more confusing. You could justify that the height of the bounce is less, okay, but the velocity is the more obvious one. Okay, so what's happened here? Let's describe having a bit more detail about energy. So let's have a think about what's happened. So let's go back to the beginning. Right, a child drops a ball. It's being dropped, it's not being thrown, it's being dropped. So that's actually important for the energy there. It's being dropped. Okay, so what's happened is that gravitational potential energy, it's either gravitational potential energy has been transferred to kinetic energy when the ball initially dropped. Okay. Then when ball bounces, we're talking about just after it bounced, kinetic energy is transferred back really. Kinetic energy is again transferred to kinetic energy, and some energy is lost to surroundings. Okay, that's what's happened there. So you do it with 4 marks. So you need to explain not just one sentence for 2 marks, like before, to explain what's happening there. Okay, number 2. Let's have a look. So a student carried out an investigation to determine the spring constant of a spring. Okay, so other things can have a spring constant, like an elastic band can have a spring constant as well. Or I saw once about the spring constant of a piece of artery, so it's not just a spring, but in this case it is. Okay, table 1 gives the data obtained by the student. We've got force in newtons, going up in 2s, extension in centimeters. So again, because it's experimental, it's a dependent variable, it's the measurement, so it's not going to be perfect because it's a real life thing. Okay, well, yeah, they thought they'd be designing an experiment. Describe a method the student could have used to obtain the data in table 1. You should include any cause of inaccuracy in the data. Your answer may include a label diagram. Okay, so let's write this. So yeah, example, because in the exam, you probably will find, because obviously you're under pressure and rushing, you'll probably find drawing a diagram may help you. in this. So let's just write it out first, then we'll draw the diagram in this case. But yeah, in exam, we're probably under more pressure than here. So probably we'll draw the diagram and then label, but we're going to write it out, okay, as well for here. So set up a clamp stand with a clamp. That's what a clamp stands for. So hang the spring, hang the spring from the clamp. Okay. So use a second clamp. Use second clamp and a boss. So a boss and a clamp stand. So if you've forgotten some equipment, if I could have a look up some equipment if you don't know what this equipment is. Okay, to fix, you could say a ruler, meter ruler. Any way of measuring is fine here. Okay, alongside the spring. Measure it. So you have to take initial recording. So take an initial recording of the length of the spring and where the spring is level with, it's at the bottom of the spring, on the ruler. I mean, you could also change the ruler's height a bit, okay, to correspond to like the, also it's on a certain number to make your life easier measuring. Okay, so you're recording where the bottom of the spring is there. So let me just put it in brackets. Record bottom of the springs is. This is the point people kind of mistake. They think that the graph is talking about the entire length of the spring, but it's looking at the extension, so how much it's stretched. So that's why you have to know where the bottom of the spring is. Okay. So then you hang a, let's see what the mass was, false. Okay, so the initial reading 0 and extension, because it hasn't stretched, is 0. Okay, it's not like a 0 centimeter spring, okay, with no dimensions. It's just extension. So at 0, no weights on it, no masses, it will be 0. So they started with 2 newtons. So hang a 2 Newton weight from the bottom of the spring. Might have a hanger. Could be a mass hanger. And then called new position of the bottom of the spring. Calculate the change. That's the extension. So how much is stretched? Easy enough. Just remembering that. So add 2 Newton weights at a time. Calculating the extension each time. Okay, so that's actually the experimental bit done. So it says sources of inaccuracy. So we could misjudge the position at the bottom of the spring. Another one, which I thought of, is that if you had masses to it, it would kind of bounce around, wouldn't it? So not waiting. If you think about in your head what would happen if we did this, waiting for spring to stop moving while taking measurement. Okay, so yeah, lots of these things that they allow quite a few different answers for. Okay, so we've got all the marks for that one. Okay, so other things you may have thought of. So misjudging it. So you could have a camera on it, couldn't you, to increase accuracy? I didn't ask that, but you could say the converse, like to increase it, you could say they have a camera set up, okay, or some kind of electronic measurement, okay, to also inaccuracies. Yeah, the experiment's not repeated there, is it? That's a big one. That's a nice easy mark, isn't it? You say, well, you repeat it because the person has only got one. They didn't say it was an average. Okay, so we can't take that to be the case. Okay, thank you for listening to this part. So I'll continue the paper on part 2. Thank you for listening. Goodbye.